Hi everyone, welcome to Mostly Math. Today we'll be talking about the Poschl-Teller Potential in the context of quantum mechanics. Pretty interesting name, Poschl-Teller Potential. And it is V of x is equal to negative lambda plus 1 over 2 sec h squared x. And the graph of this function looks like this. We have asymptotically approaching x-axis going out, some value coming back. This is 0, of course. Excellent. What's interesting about this is that we'll find that if we put it into the time independent Schrodinger equation, we'll actually find an analytic solution, which is very unusual for such an unusual potential. Recall the TISE from the previous video. H psi is equal to E psi, or minus h bar squared over 2m d squared psi by dx squared plus v psi is equal to E psi. And we can go ahead and use units where m is equal to h bar is equal to 1. We can do this because it's just saying that all masses are measured in terms of the particle's mass, like how heavy is that basketball? Well, it's 1,000 times the mass of this particle. How much energy does it have? Or action, rather? Well, it would be 150 times the action of this particle. Fine, not a problem. So we have minus 1/2 psi double prime of x plus v psi is equal to E psi. We're also using the prime notation because we'll see that the solution is a special function, and that's much more common in the special function literature. So now we're just going to write down the differential equation for our specific potential that will be occupying us for the rest of this video. Plugging our potential into this equation here. And it'll tell us that minus 1/2 psi double prime of x minus 1/2 lambda plus 1 sec h squared x psi is equal to E psi. Rest of this video we'll be solving this differential equation. And we're going to do that by a common technique of U substitution. We're going to let u be tan h of x, and then obviously x is equal to inverse tan h of u. So basically, we have to know a bit about the inverse hyperbolic tangent function to proceed with this. We'll be using identities which we'll be proving, like sec h squared tan h inverse of x is equal to 1 minus x squared. Not that hard, we'll see. And the derivative of tan h inverse x is equal to 1 over 1 minus x squared. Excellent, we see 1 minus x squared in both quantities. A clue that something good could happen. First step is to transform the potential here from x space into u space. That's pretty straightforward. So we have sec h squared x just corresponds to this identity here. Sec h squared tan h inverse of u. And this is just 1 minus u squared per the above identity. Now we'll transform the derivatives first. So by taking differentials of both sides of this equation, we have dx is equal to d tan h inverse of u, which is simply du over 1 minus u squared for this expression here. But we really want d by dx because we have psi double prime. Not a problem, just take d over both of the sides. So it tells us that d by dx is equal to 1 minus u squared, d by du. Excellent, now we'll transform psi double prime to be just this operated on psi twice. Not a big deal. 1 minus u squared d by du 1 minus u squared d psi by du. Using the prime notation here again, it's going to be 1 minus u squared times 1 minus u squared psi prime of u prime. Now we can just insert this and this into our expression above to obtain the differential equation. Not a problem. Just need some more room to display it. Okay. So the u space differential equation is going to be 1 minus u squared psi prime of u prime plus lambda plus 1 psi plus 2e over 1 minus u squared. Psi is equal to e psi. Did a brief simplification here. Basically, I just multiplied everything by 2 and moved this to the other side at the cost of a minus sign. Yep, just making sure I did everything right. You see the secant h squared term has been absorbed into there, so everything's okay. I'm just going to make one more simplification as well. Let's go ahead and get rid of this side. And just put this term in brackets here. Before we move on, let's go ahead and prove the identities that we talked about earlier. So we'll be starting with the hyperbolic tangent identity, hyperbolic tangent identity. 1 minus tan h squared is equal to sec h squared. So if we recall, we let u be tan h earlier. So then it tells us that 1 minus u squared is equal to sec h squared tan h inverse of x, since x was just inverse h tan. Okay, got that. The other one, I don't really see this in books, but this is how I recall the following expression. So we know that integral of 1 plus x squared is equal to the ordinary inverse tangent of x. So we're just going to let x go to ix here. So we get I integral of dx over 1 minus x squared is equal to tan inverse of ix, which, if we recall anything about the hyperbolic trig functions, if we put ix in the ordinary trig, we get the hyperbolics with a cost of an I at this time, tan h inverse of x. So this tells us that the integral dx over 1 minus x squared is equal to tan h inverse of x. And of course, if you want to, you can just take derivatives of both sides to obtain the identity in the form that we discussed earlier with the derivatives instead. But that's just how I remember it. There are other proofs in calculus books using the implicit function theorem. There's a lot of ways to go. Okay, let's continue with our main expression here. So, where was I? We want to recognize this as a special function. In particular, if you have studied the Legendre functions, they are denoted p lambda mu of x, and they satisfy a very similar differential equation. They satisfy this one. 1 minus x squared p lambda mu of x prime plus lambda plus 1 minus mu squared over 1 minus x squared p lambda mu is equal to 0, which looks extremely similar to our expression up above. In fact, we can make it be the same by a choice of our constant E, which is the energy of the system, or the eigenvalues. Basically, by comparing these and choosing E, we have solved the system. We have actually found that psi of u, since we're in u space, is, substitution psi tan hx, which is just p lambda mu of tan hx. And the p lambda mu's have a few conditions that go along with them. So if we want them to be the same, we need the E to be minus mu squared over 2 with the following conditions on lambda and mu. So lambda is just a positive integer, but mu is a positive integer that cannot exceed lambda. We'll see this graphically in a moment. It's not as esoteric as it sounds. Yeah, let's just go ahead and graph the function so we see what we're talking about here. Well, I'm actually going to graph the potential. You can feel free to look up the graphs of the Legendre functions if you want. They're not that exciting. They don't really tell us a lot about the system, at least at this level. Okay, but let's go ahead and perform a standard analysis in quantum mechanics. We're going to draw the graph of the potential, and then we're going to put its eigenvalues in. So this was x, this was v of x, of course. Let's go ahead and put a few eigenvalues here. So if we start with lambda equals 1, have minus 1/2, that's the first eigenvalue, minus 1/2. Next eigenvalue is going to be minus 2 squared over 2, which is just minus 2. Spacing's increasing a bit here. Next one, minus 9/2, spacing increasing more. Finally, last eigenvalue that fits on this graph is going to be minus 8, and we're done. So basically, the interpretation of these conditions is draw the potential, start at the top, fit as many eigenvalues as you can, and you're done. That's how many energies that the system will allow. And I think it's interesting because we do have an analytic solution in terms of special functions for a very unusual potential. Doesn't always happen in quantum mechanics. And if you enjoyed this, want to see more, please subscribe. I'll see you next time.